Okay, so let's start then. Okay, so we were talking about the Laplacian on a Riemannian manifold. So we saw it's the divergence of the gradient vector field of a function. And we also saw that it is the trace of the Hessian of the function. And then we derived a change of variables formula for the Laplacian and also a product formula for the Laplacian. And we proved Green's formula for the Laplacian, which is very important in the study of harmonic functions and the Laplacian. And then we saw using, essentially using Green's formula, we saw that the Laplacian defines a densely defined symmetric and negative operator on L2 of M, where this L2 is with respect to the Riemannian volume measure. Yeah. So it's a symmetric and negative operator. And so it has a self-adjoint extension called the Friedrichs extension. And then we stated Gaffney's theorem that for a complete Riemannian manifold, in fact, it has a unique self-adjoint extension. Okay. And so the extension is also a negative operator. And so the spectrum of the Laplacian is contained in the interval -infinity to 0. Okay. So here let me make a remark about what I left unfinished last time, which is this example of a self-adjoint extension of the operator, let's say the Laplacian in one dimension. So that's just d squared dx squared acting on CC infinity R, which is a dense subspace of L2R, mapping into L2R. So here, let me describe the self-adjoint extension. So we have this example. So take S to be d squared dx squared. Okay. So the right domain of the self-adjoint extension is actually the following. So you define, say, E to be the set of U in L2R. Such that the second distributional derivative is also in L2R. So this here, this is a distributional derivative. So this is in the space D star. Yeah, this is the space of distributions on R. Okay. And then you define the operator T from this dense subspace E in L2R to L2R. U maps to its second distributional derivative. Okay, this is the distributional derivative. Okay. Now, what is the domain of T star, right? So a function U in L2 of R is in the domain of T star if and only if the inner product of, well, the linear functional V in the domain of T, which is equal to E, maps to inner product TVU, which is equal to the integral of V double prime times U dx, right? And see, by definition of the distributional derivative, this is equal to the second distributional derivative acting on V if V belongs to CC infinity R, right?
Yes.
Okay. This is by definition of the distributional derivative, right? Okay. So U is in the domain of T star if and only if this linear functional is bounded, right? Okay. So clearly, if U belongs to, so if suppose this is bounded, then in particular this is bounded on CC infinity R. So that means that the second distributional derivative is bounded on, so this implies that mod d squared U dx squared U dx squared acting on V, this is less than or equal to a constant times the L2 norm of V, right? For all V in CC infinity R, right?
Yes, sir.
But this happens if and only if, this happens if and only if this distribution is actually in L2, right? Yes, a distribution satisfies such an L2 estimate if and only if it actually belongs to L2, right?
Yes. Yes.
This is a standard fact about distributions, right?
Yes.
So if U is in the domain of T star, then it follows that U belongs to E, right? Okay.
Yes.
And the converse is also easy to see. If U belongs to E, then that means that d squared U dx squared U, this distribution is in L2, right? It's given by an L2 function. And then this integral is just V time. By definition, this distribution acting on V is just this L2 function times V, that integral, right? Yes?
Yes. Yes.
And since this d squared U dx squared is in L2, then this integral will be bounded by Cauchy-Schwarz, by the L2 norm of this d squared U dx squared into the L2 norm of V. So that means this will become a bounded linear functional, right?
Yes.
So that means that U will belong to the domain of T star. Okay, so therefore we get that U belongs to the domain of T star. So I'll just write conversely, if U belongs to E, then d squared U dx squared U belongs to L2R, and for all V in CC infinity R, the inner product TVU this is equal to d squared U dx squared acting on V. This is equal to the integral over R of the L2 function d squared U dx squared into V. This is less than or equal to the L2 norm of d squared U dx squared into the L2 norm of V. Okay. And since this is true for all V in this dense subspace, it's going to be true for all V in the domain of T as well, right? Okay.
Yes.
And so this implies that by definition, U belongs to the domain of T star. Okay. Therefore, the domain of T star is equal to the domain of T, which is E. Okay. And for all V in CC infinity R, and U in the domain of T star equal to domain of T. the inner product TVU, this is equal to, as we've seen, d squared u dx squared acting on V. And since this belongs to L2, this is, as we've seen, this is the integral of d squared u dx squared into V dx. And this is the inner product of V with TU. Okay, right? So therefore, by definition of the operator T star, right, it follows that T star of U is equal to T of U. Is this clear?
Yes, sir.
All right. So therefore, T star is equal to T on the common domain, right? So therefore, this operator is self-adjoint. Is this clear?
Yes, sir.
Yeah. Orkojit, is this okay? Rudra,
Yeah, Kingshuk,
is this-
in this, yeah.
yes.
So in this case, you are not using this essentially term, right?
No, in this case, I mean, it's true that this is essentially self-adjoint because this is the Laplacian in R, which is a complete manifold. So by the general theorem, we know this is essentially self-adjoint. But I mean, the point is here we can explicitly construct the self-adjoint extension, the unique self-adjoint extension.
Okay.
We're explicitly constructing the domain of the extension. It's this domain, right?
Yeah. Yeah.
This domain, yeah. So I have a question which I'm not sure of. I was thinking about this. I'm not sure if the answer is yes or no. You see, normally the Sobolev space W2, 2, that would be defined as U in L2 such that U prime and U double prime are both in L2, right?
Right.
Now,
Yeah.
here we are only defining U double prime in L2.
Is equals to W2, 2, sir.
Yeah.
If U double prime is in L2, I'm not sure. Does it imply that U
Yeah.
prime is?
Yes, sir. If U and U double prime is in L2, it would follow U prime is in L2 because of Plancherel theorem.
Ah, I see. I see.
Yeah, that's
So-
true. You can use Plancherel theorem. Yeah.
What I was thinking is an integration by parts. You see, if I want to show that U prime is in L2, so I'm looking at integral of U prime squared, right? So suppose U is in CC infinity first, then by integration by parts, this is minus the integral of U times
Yeah, we
U.
understand. Yeah. So you are getting U double prime U.
Right. So this is in L2 and this is in L2. So this integral is finite.
Right.
So therefore, this integral is finite. Does that make sense? That should work, I think.
Yeah, I think so. Yeah, this is also good argument. Yeah.
This should work, I think, right? So, yeah.
Oh, so there's no point in taking U prime.
I guess, yeah. So the
Mm.
domain, so maybe I should put in brackets. This is the same as U such that U prime, U double prime are in L2, which is equal to W2, 2. Okay. I think this is correct, right? Yeah.
Yes, yes.
All right. So what we get here is actually just the unique self-adjoint extension. It turns out the domain is the Sobolev space W22, and the operator is given by the distributional derivative acting on this Sobolev space. Okay, that's the self-adjoint extension. Yeah.
Yeah.
Okay, good. So I guess on a Riemannian manifold, you can do something similar. you see. You look at the space of distributions on the manifold, and I mean, I haven't worked this out, but I think you can do something similar. To construct a self-adjoint extension, it should be, the domain should be a Sobolev space. The domain should be a Sobolev space. And the operator will be given by the distributional Laplacian. So
Right.
that should be the self-adjoint extension. I think, you know, this example should generalize to a manifold. But yeah, I haven't worked that out. I'm just guessing it should be similar. Yeah. Okay, so I just wanted to make this comment. So now let's come back to any questions? Utsav Rudroda, is this fine? Yeah.
Yes, sir.
Yeah.
Okay. This is okay. Okay. All right. So yeah. So then, okay. So then we worked out the Laplacian in local coordinates using the expression for the gradient in local coordinates and also for the divergence in local coordinates. And we saw that it's a second order elliptic operator, right? So that means these partial derivatives, del squared f, del xi, del xj, their coefficients are given by G upper ij, which is a uniformly positive definite matrix on any compact domain in my manifold. Right? So uniformly positive definite means that it satisfies this estimate. So for any vector v in Rn and any point P in the compact domain D, the quadratic form sum over ij, Gij P, Vi, Vj, this is greater than or equal to some positive constant epsilon times the norm of the vector v, summation over I Vi squared. So this is equivalent to saying that the smallest eigenvalue of this symmetric matrix is greater than or equal to epsilon, right? Okay. Yes, that is clear. Yeah.
Yes, sir.
So then we say that such a second order operator is an elliptic operator. Okay. So on any compact or pre-compact subdomain of our manifold, the Laplacian is an elliptic operator, a second order elliptic operator. Okay. So now I suppose of course, all of you are familiar with the mean value property for the Laplacian in 2 dimensions. Well, there you can prove it using Cauchy integral formula, right? Since harmonic functions are the real parts of holomorphic functions, and you can, the mean value property follows from the Cauchy integral formula in 2 dimensions. In higher dimensions, the proof I know uses Green's formula and the Green's function. So we'll do a version of that for harmonic manifolds. So you know that harmonic functions satisfy the mean value property. So the Laplacian is closely related to the mean value operators, right? So in a general Riemannian manifold, this relation becomes a bit more complicated. We still have a nice relation for what are called harmonic manifolds, which I'll define in a while. But for a general Riemannian manifold, we don't have an immediate relation between the Laplacian and the mean value operators on spheres. What we do always have is the following. We have a relation between the Laplacian and what you might think of as an infinitesimal mean value. So that means the mean value on very small spheres, okay, with radius tending to 0. So we're going to prove such a relation now. So first, let's start with this lemma. So let lambda be the Lebesgue measure on the unit sphere Sn minus 1. Okay. So let's normalize it to have a mass 1. So just rescale it to make it a probability measure. All right. Okay. So this lambda is just the Riemannian volume measure of Sn-1 divided by the volume of Sn-1. Okay, so this is a probability measure. Then the first point is that the integral over the unit sphere of any linear function of v is 0 with respect to this measure lambda. Okay, so this integral is 0 for any linear function L on Rn to R. Okay. And secondly, if I take a quadratic form, so a quadratic form is of the form inner product AVV, where A is a symmetric linear map. Okay. So if I take the integral of any quadratic form over the sphere with respect to this probability measure, the Lebesgue measure, then we get 1 over n times the trace of A. Okay. So the trace you can also see as given by integrating the quadratic form over the unit sphere. All right. So you can write the trace as an integral. I mean, this is something which I don't know. It should be taught, I think, in a linear algebra class, but it's never taught. Anyway, so it's an elementary fact. So we'll prove this. Okay. So so for the first part, this just follows from the fact that linear functions are odd functions, right? With respect to the antipodal map, v goes to minus v, right? So if I take this antipodal map I from the unit sphere to itself, v goes to minus v. Then first of all, this Lebesgue measure is invariant under this antipodal map, right? So lambda of I inverse u is equal to lambda u for any Borel's subset of the sphere. And secondly, so this linear map is an odd function with respect to this antipodal map, right? So L of minus v is minus L of v. So that will, the integral over any odd function over the sphere will be 0, because this integral, what I can do is I can make a change of variable, right? I put a new variable w equal to I of v, right? So when I make this change of variable, and then I write v again for the variable w. So when I make this change of variable, this L of v will become L of IV, and this d lambda v will become d lambda IV. But that's the same as d lambda v, because this measure lambda is I invariant, right? Yes?
Yes, sir.
So this becomes L of IV d lambda v, and L of IV is minus L of v. So you get that this integral is equal to minus the integral. Therefore, this integral is 0. Is this all right? Yeah.
Yeah.
Okay. All right. Now for the quadratic form. So you take the symmetric matrix A. So then we use the spectral theorem. So we can write A as T star delta T for some diagonal matrix delta with eigenvalues lambda 1 to lambda n and some orthogonal matrix T. So then this quadratic form becomes diagonal, right? Once you use the corresponding basis of eigenvectors. So this inner product AVV, I'll write this as inner product T star delta TV with V. So the T star I can take to the other side. So this becomes inner product delta of TV with TV, right? So now the point is to think of TV as a new variable, right? So
Yes.
T is an orthogonal linear map, so it maps the sphere to itself. And since it's orthogonal, it preserves the Lebesgue measure lambda, right? The Lebesgue measure lambda is invariant under the orthogonal group. So we can make the change of variables W equal to TV in this integral, right? Okay. So this integral of AV inner product V d lambda V, this is an integral of delta TV with TV d lambda V. So when I make the change of variables W equal to TV, then this becomes the integral of delta W W d lambda W, right? Okay.
Yes,
Yeah.
sir.
Okay. And now this delta WW, this is just a diagonal quadratic form because delta is a diagonal matrix. So this is just a sum of squares, summation lambda I Wi squared, right? Okay.
Right.
But now Wi squared is what? This is the integral of, this is the inner product of W with EI squared, right? And so if I take any other J, then I can always take an orthogonal linear transformation which maps EJ to EI. So T inverse of EI is EJ. And then what I do is this integral of Wi squared. So that's integral W inner product EI squared. I make the change of variable W equal to TU. All right. And so then this W becomes a TU inner product EI. And the measure is unchanged because T is an orthogonal transformation. Okay. And so then this becomes integral of U T star EI. And T star is T inverse since T is orthogonal. And T inverse of EI, I've chosen this orthogonal matrix so that T inverse maps EI to EJ. So this becomes integral of U inner product EJ squared, right? D lambda U. So what that means is that these integrals of the Wi squareds, these are equal for all I, right? And that you can see, of course, by symmetry, right? It's just the integral of the Wi squared coordinate is going to be the same as Wj squared coordinate because you have an orthogonal change of variables which takes the Wi coordinate to the Wj coordinate. That's all.
Yes.
Now these integrals are equal. So if I call them equal to C, for example, then what do I have? I know that on the unit sphere, summation Wi squared is equal to 1, right? So therefore,
Yes.
I get 1 is equal to the integral of summation Wi squared d lambda, because this lambda is a probability measure. And this is equal to n times c, because each of these integrals are equal to c. So this is equal to n times c. So that means this constant c is 1 over n, right? So each of these integrals of the Wi squared is 1 over n. And so therefore, my integral of AVV, this was the integral of summation lambda I Wi squared. So this becomes c into summation lambda I, and c is 1 over n, and summation lambda I is trace of A. Okay. Is this all right? So this integral is just 1 over n trace of A.
Yes.
All right.
Yes, sir.
Okay. So now we can use this to prove the following infinitesimal mean value property for the Laplacian. So, okay. So first of all, we want to do a second order Taylor expansion of a function on a Riemannian manifold. So how do we do that? So what we can do is, we can, if we take a point P, then we can look at the function f tilde, which is f composed with the exponential based at P. So this then becomes a function on a vector space, TPM, right? Okay. This is a smooth function on a neighborhood of 0 in TPM. Okay. So, so now it's a function on a vector space. For a function on a vector space, I have the usual Taylor formula, right? So I can use the second order Taylor expansion of f tilde. That will give me a second order Taylor expansion of f. All right. So that's the idea. So to compute the second order Taylor expansion, we have to compute the first and second derivatives of this function f tilde on the vector space TPM at the point 0. All right. So what is the derivative of f tilde at 0? So acting on a vector v, by the chain rule, this is ddt at t equal to 0 of f tilde of tv, right? But now what is f tilde? F tilde is f composed with the exponential. So this is ddt at t equal to 0 of f of x tv, right? But XTV, this is a geodesic with initial velocity equal to V, right? So by the chain rule, this is just df acting on V, df at P acting on V, right?
Yes, sir. Fine.
Okay. So
Yeah.
that gives us the first derivative of f tilde at 0. Similarly, the second derivative of f tilde at 0, this we know from our Euclidean analysis. This is the second derivative of f tilde along the straight line TV, right? But now the second derivative of f tilde along the straight line TV, by definition of f tilde, this is the second derivative of f of x of TV, right? And that's the second derivative of f along a geodesic. So that we've already seen, that's equal to the Hessian of f acting on V, right?
Yes, sir. Right.
This we've already proved. This is the Hessian of f acting on V. So that means the second derivative of f tilde at 0 is nothing but the Hessian of f at P. Okay. And so therefore, by the Taylor formula for functions in Rn or in any vector space, so we have a epsilon positive and a constant C positive such that f tilde f of x V, that is f tilde of V, I can write this as f tilde 0 plus df tilde 0 acting on V plus half d squared f tilde 0 acting on VV plus some error term of V for all V of norm less than epsilon, where this error term by the Taylor formula is of order norm V cubed, right? Okay, so this is less than a constant times norm V cubed, right? This is what the Taylor formula gives me. And now I substitute what is this f tilde of 0. This is just f of P. Df tilde at 0 of V is just df PV. And d squared f tilde at 0 of VV. This is just the Hessian of f at P acting on V in a product with V. And then plus this error term. Is this all right? Okay.
Yes, sir.
Yes, sir.
So I have this second order Taylor expansion for any function in a Riemannian manifold in a neighborhood of P, right? Okay. And now using this, we can prove the following proposition relating the Laplacian and the infinitesimal mean value. So what is this? So first, let lambda P be again the normalized Leibniz measure on the unit sphere in the tangent space. Okay, so this TP1m, this is the unit sphere in the tangent space. All right. So it has its Riemannian volume measure, right? And I divide by the volume of TP1m. So this is the normalized volume measure on TP1m. Okay, so this is a probability measure. Okay. Sorry, so we got disconnected. All right. Okay, fine. So now, right. So we have this normalized probability, this probability measure on the unit tangent sphere, okay, in the tangent space. So for T small, we can define a mean value, MTFP. This will be a certain mean value over the sphere of the geodesic sphere of radius T. So how do I define this? This is the integral over the unit tangent sphere, TP1n, of f of xptv d lambda p. All right. So this is an average, a mean value of f over the geodesic sphere of radius T, right?
Right.
Okay.
Yes.
And the proposition says that if I take this mean value minus the value of f at P and then divide by T squared, then this converges to 1 over 2n times the Laplacian of f at P. Okay. So the Laplacian you can interpret as a limit of the mean value around small spheres minus the value of the function divided by t squared, the radius squared. All right. Okay. So, I mean, before we do the proof, any questions about or comments about this statement?
So if the Laplacian is 0, then
So if the Laplacian is 0, that means that the mean value is going to be 0 up to second order, right? Up to
Okay.
second order.
right. Yes.
I mean, the mean value is not 0. I mean, the mean value is going to equal the value of the function up to second order. Okay. See, the thing is, the mean value always equals the value of the function up to first order. That means this empty fp, it equals f of p plus something of order t squared.
Mm.
So there is no order t term. At first order, it actually always equals the value of the function. The point is, if the Laplacian is 0, then the second order term is also 0 in the expansion of mt with respect to t. All right. So a harmonic function, that means one whose Laplacian is 0, that you can think of as satisfying an infinitesimal mean value property up to second. Okay. Okay, so how do we prove this? So the proof is, so we look at this integral defining the mean value. So this is an integral of the unit sphere f of x dv. Now we use the second order Taylor expansion that we had over here, right? F of x v is of this form. F of x v is fp plus dfpv plus 1 over 2 into the Hessian plus an error term. So we substitute this Taylor expansion into the integral, right? So this becomes f of p plus dfp tv plus half the Hessian f acting on tv plus an error term of tv d lambda p, right? So now when you integrate, since this is a probability measure, f of p comes out of the integral, and then since dfp is linear, this t comes out of the integral, and then you get the integral of dfpv d lambda p, right? So this integral vanishes because dfp is a linear function. So by the part 1 of the previous lemma, this integral vanishes, right?
Right.
So that's
Yes.
why there's no order t term, you see? That's why there's no order t term. The order t term vanishes because the derivative is a linear function, it's an odd function. So the first term in the Taylor expansion is going to vanish, all right?
Yes.
When you
yes.
okay, so that's why there's no order t term. But now there is an order t squared term, right? So the order t squared term is the integral of the Hessian, right?
Mhm.
But
Yeah.
we know what this integral is. This is 1 over n times the trace of the Hessian, right? And
Yes.
the trace of the Hessian is just the Laplacian, right?
Mm.
And then there's a error term, but the error term is going to be of order t cubed, right? Because this error term e tilde, this is the integral of e of tv, and so mod e tilde is less than or equal. This e of tv is less than or equal to a constant times the norm of tv whole cubed, right?
Mm.
So this becomes just c times t cubed. So that means this error term is of order t cubed. Okay, so you get finally f of p plus t into 0 plus 1 over 2. There should be a 1 over n here. There's a typo. There's a 1 over n, and then t squared into the trace of the Hessian plus an order t cubed term. So yeah, this is the right thing. So f of p plus half t squared into Laplacian f at p divided by n plus e tilde. So now you just take this f of p to the other side, divide by t squared, And so then this converges to 1 over 2n into the Laplacian.
Hmm.
And this e tilde term goes to 0 because it's of order t cubed. So when you
Right.
divide squared, it will go to 0. Right?
Right. Yes.
Is this all right? Yeah.
Yes, sir. Fine.
Yes.
Okay. So yeah. Okay, so you can interpret the Laplacian in terms of infinitesimal mean values.
Yes, so sir, in case of this, here we are working on a general Riemannian manifold, right?
Right. This is on a general Riemannian.
And a general Riemannian manifold, we have this infinite Riemann property only on infinitesimal level, contrasted with the case
Right.
of harmonic manifolds where we
Right.
have,
Yes. Yes. Yes.
okay. And one other question, actually from the last step that you said, that when we're looking at these manifold, Riemann manifolds, there the Laplace Beltrami is not uniformly elliptic, right?
No, it's not uniform. Unless if it's a compact manifold, then yes. It's uniformly elliptic. On a compact manifold, it's uniformly elliptic.
Okay, so yeah, so like again, contrasting with the case in the Euclidean space or also in the compact case. So I want to understand like that epsilon factor that is the uniform ellipticity constant that goes to 0 as you were saying last time. So how does like can we relate that with the curvature? I mean, like in specific curvature, how far is it from being uniformly elliptic? The rate of epsilon going to 0 with respect to the curvature. Can you say something like that?
We can, yeah. So see, the coefficients with respect to coordinates are just Gij, right? G upper ij, okay.
Yes.
Right, the inverse of the matrix G lower ij, which is the matrix of the Riemannian metric. Now, what is yeah, so suppose I take, let's say, geodesic normal coordinates based at the origin, okay, in a negatively curved manifold. All right. Okay, so suppose k is less than or equal to minus a squared. All right. And I take a point P and M. And I take x1 to xn or geodesic normal coordinates around P. All right. Yeah. So what are the Gijs? So here's my point P. And if I take a point Q, right, what is Gij? G, yeah, so let me just think of how to do this nicely. So okay. Let me look at the quadratic form itself. Yeah, let me just look at the quadratic form. So let me take a vector V in Rn. Okay. And let me look at inner product, capital GQ VV, right? Yeah.
Yes.
So what is this? This is basically this is the norm of the vector summation Vi del xi at Q, right? This norm squared. Yes?
Yes.
Okay. Now, how can we estimate this norm? So, Mm. Right, so I'm taking a vector here. So, so let me call this vector, say W. Okay, so W is equal to summation Vi del del Xi Q. So this is in TQM. So here is W. And yeah, so, okay. Right, so, okay. So what is this? This is, so this W vector, okay, so this is norm W squared, fine. This is norm W squared. Now, what is W? This summation Vi del del Xi at Q. This is equal to the inverse of, so this is equal to ddt at t equal to 0 of phi inverse of, so let me call, let's say, what should I call it? Say y equal to phi of q, okay? So this is a point in Rn, right? Okay. So this is going to be ddt at t equal to 0, phi inverse of y plus tv, right? Yes.
Yes.
Okay. Now, what was phi? My geodesic coordinates are how? How are they defined? Basically, I'm taking the inverse of the exponential, okay, into TPM. And then I'm taking a linear isometry, T, right, to Rn. This is how my geodesic normal coordinates are defined. Yeah.
Yes.
So what will phi inverse be? So phi here is T composed with XP inverse. So phi inverse, this is going to be ddt at t equal to 0 of XP of T of y plus TV, right?
Yeah.
Okay. Yeah. So so this is ddt at t equal to 0 of so let me call T of y is some z, let's say, and T of v is some I don't know, some other vector, say u. Okay. So here, so this is tu. So z belongs to, so z is equal to ty, which belongs to TPM, and u is also equal to TV, which belongs to TPM, right? Okay. So by definition, this is what? This is the derivative of the exponential map at z applied to u, right? Okay.
Yes.
Yes. Yeah. So now, yeah. Okay. So what is norm Z? Norm Z is equal to
DPQ.
it's just dpq, right? Z is equal to just xp inverse of q. So norm Z is equal to dp of q, right? Okay. And so this, so let me call this, say a radius r. Okay. So this distance is r here. Okay. And so then, so I can write this in terms of the value of a Jacobi field at time r, a Jacobi field along a unit speed geodesic. So if I write Z as say r times a unit vector, what should I call it? I don't know. I've used up WX. Oh, no, I haven't used X.
Z cap.
So R times some X, let's say. X is a unit vector. Okay. Then this right. So then what is the picture? I have basically P, and then I have, this is Q equal to X Rx. Okay. And use TV. Right. So then I'm taking a one parameter family of geodesics here. Right, where this will be, so I define gamma S of T is XP of T X plus S. So what is my vector in the tangent space? U, right? Right. So if I look at this one parameter family of geodesics, and then I define J of T is, so this is my F of ST. So then J of T is del del S at S equal to 0 of F of ST. And J0 is 0. And J prime 0 is J prime 0 is going to be U, right? Yeah.
Yes, sir.
Yes, sir.
Okay. So then what is I see. So yeah, so what is J of R? J of R is going to be del del S at S equal to 0 of XP of, so this T becomes R, so Rx is Z plus RSU. So this is going to be R times W, right? Okay. So W, yeah. So we get this estimate. So W is equal to J of R divided by R, right? Okay. So this norm W squared, okay. This is going to be this norm of the Jacobi field squared over R squared. So this is greater than or equal to A squared sin H squared AR into the normal component of W. Yeah, right. Yeah. Sorry, the normal component of U. The normal component of U. U is the initial thing. Right? Divided by R squared. Okay.
Yes.
So that means that this this was my quadratic form, right? GQ W GQ VV, sorry, GQ VV, right? So that means the norm of this quadratic form, this is going to grow exponentially in the directions which are orthogonal to the geodesic passing through Q. So in these orthogonal directions, the norm of my quadratic form is going to grow exponentially. In this direction, it will be constant, equal to 1. All right. So that means the matrix G, if I take coordinates at this point, which are, yeah, well, so, I mean, so when I so that means the eigenvalues of G are going to be 1 and, I mean, lambda i's, which look like e to the 2 AR. Okay, well, divided by R squared. I goes from 1 to n minus 2 to n minus 2 to n, right?
Yes.
Okay, so when I take the inverse, so this is my matrix G. These are the eigenvalues of G. So when I take G inverse, that means the G inverse, the eigenvalues will be exponentially small, except for one of them, right?
Yes.
So that means my coefficients G upper Ij's are going to decay exponentially, like e to the minus 2 AR. So, okay.
Yeah.
Does this make sense? Yeah.
Yes. Yes.
Right.
So if it is like the curve is bounded above by some negative square term, so it's going to be exponential. The universe constant converges to 0 exponential.
Right. So I mean, so that means that the eigenvalues of G inverse are 1 and lambda I inverse, right? Which is
Yeah. Right.
these are the eigenvalues of G inverse. So that means G inverse is, by the spectral theorem, T inverse or T star into a diagonal matrix 1 and things which looks like e to the minus 2 AR, e to the minus 2 AR t, right?
Yes.
Okay. Is this all right? Yeah.
Yes, sir.
Okay, so this gives you, so the smallest eigenvalue is small, right? Is e to the minus 2 AR. Well, into R squared, but okay. The exponential kills the polynomial, so yeah. All right.
Yes, yes.
Okay, so the coefficient of ellipticity, that's the smallest eigenvalue, right? So the smallest eigenvalue is going to 0 exponentially.
Yes, sir. Yes, it's clear now. Yes.
Okay, is this clear? Yeah.
Yes, sir.
So that's why, yeah, it's not going to be uniformly elliptic on the whole manifold. So that's why you have to restrict to a compact subdomain. Yeah. In general, whenever you have some negative curvature, then basically the G lower ij's will grow exponentially. And so the G upper ij's will decay exponentially.
Right, right.
That's it. Okay, so any other questions about this infinitesimal mean value? Any questions? Yeah. So see, in Rn, we know that harmonic functions satisfy the global mean value property. But harmonic, by definition, means that I mean, by this proposition, it means that that f satisfies the infinitesimal mean value property up to second order, right? Yeah. So in fact, in Rn, you get the fact that if you satisfy the infinitesimal mean value property up to second order, then you satisfy the global mean value property, right? Is that clear?
Yes.
Okay, so the infinitesimal mean value property implies the global mean value property. So that's true for Rn. And now we're going to see that's also true for a larger class of manifolds called harmonic manifolds. Okay, so now finally we come to the topic of the course, which is harmonic functions on Riemannian manifolds. All right, so we have a Riemannian manifold M, and delta is the Laplacian of M, which is divergence of the gradient. So for any open set U and M, we say a C2 function f on U is harmonic if delta f is 0. We say it's subharmonic if delta f is greater than or equal to 0. And we say it is superharmonic if delta f is less than or equal to 0. Okay. So this is just like the definition in Euclidean space, right? So, okay. All right. So before proceeding further, I want to compute the Laplacian of the distance function in terms of what we define to be the Jacobian of the manifold. All right. So remember the Jacobian of the Riemannian manifold M. One second. So the Jacobian of M was a function on the unit tangent bundle cross 0 infinity j of v comma r, which was defined to be the determinant of a map d phi r at the point v. So, okay, let me just, there's a lot of notation here. So here v is a point in T1m, the unit is a unit tangent vector. P equal to pi of v is the base point of the vector v. R is a positive number. Gamma v is the unique geodesic with initial conditions p comma v. So it's a unit speed geodesic. This map phi r this is the map from the unit tangent sphere at P to the geodesic sphere of radius R around P, which is W goes to XP of RW. All right. So, so what we're looking at is the derivative of this map phi R at a vector V. And then, so where is that derivative defined? It's defined it goes from the tangent space to the unit tangent sphere at the point V, right? Now, the tangent space to the unit tangent sphere at a vector V, the tangent space is going to be the orthogonal complement of V, right? Yes?
Yes.
Okay, because I mean, this is just your, I mean, whatever high school geometry, right? The radius is perpendicular to the sphere at any point. So, right? So, yeah. So that the tangent space to the sphere is just the perpendicular to the radius vector. So it's V perp. And this maps to the tangent space to the geodesic sphere. And by the Gauss lemma, the tangent space to the geodesic sphere is just the orthogonal complement to the radial geodesic, right? Gamma V, right? So the tangent space to the sphere is gamma V prime R perp. All right. Yeah, this is clear. Okay.
Yes.
So you take this linear map between these n minus one dimensional vector spaces, and then you take its determinant, right? These are inner product spaces, so I can take its determinant, right? Okay. So I take this determinant, and this is defined to be J of V comma R. Okay. All right. So, okay, we're assuming for simplicity here that the exponential map is defined on all of TPM, on all of TPM, so that M is complete. And we're assuming it's a diffeomorphism for all P. Okay, so, yeah. So these are just simplifying assumptions. Otherwise, for each V, you would have some radius R, the injectivity radius at P and so on. And so the domain of this Jacobian would become a more complicated set, right? It wouldn't be a product like this. That's all. Is that all right? Yeah. So just for simplicity, we're assuming that the exponential map is a diffeomorphism at each point P. Okay. So this is true for Hadamard manifolds, right? So those are the kinds of manifolds we'll be interested in anyway. So complete simply connected of non-positive curvature. Okay. All right. So now we want to get a simpler formula for the Jacobian. So first of all, if we take a point P and M, and then I take a vector W in TPM, let me define a function G on the tangent space TPM. By G of W is the determinant of the derivative of the exponential map at W. Okay. So where does this derivative go from? So the derivative of the exponential map at W, this goes from the tangent space at W to the whole tangent space. But the tangent space is a vector space. So the tangent space at W to TPM is identified with TPM itself. So this goes from TPM to the tangent space at the point XPW of M. All right. And we're taking the determinant of this derivative of the exponential. All right. So clearly this G is a smooth function on all of TPM, and G of 0 is 1 because the derivative of the exponential map at the origin is the identity, right? Okay.
Yes, sir.
Yes, sir.
So now we want to show that this Jacobian of V comma R, this is equal to R to the n minus 1 into G of RV. Okay. So how do we get that? Well, that will follow from the chain rule. So remember, this J of VR is the determinant of the derivative of this map phi R V goes to X RV. So that is a composition of two maps, right? I can write it as the composition of the maps. Let me call this map T sub R. This is a scaling from the tangent space to itself, a scaling by a factor of R. V goes to RV. All right. So I have this scaling and then I compose with the exponential map, right? So phi sub R, this is equal to the exponential composed with this scaling TR restricted to the unit tangent space, okay? And now this scaling, if I look at it restricted to the unit tangent sphere, then the determinant of this linear map is just R to the n minus 1, right? Okay. Yes, because this is a n minus 1 dimensional. The tangent space here is n minus 1. So there should be a dTr here. It's the derivative of tr. So, so this will be R to the n minus 1, right? This TP1M is n minus 1 dimensional, right?
Yes.
And this is a scaling by a factor of R. So the determinant on the whole space is R to the n, but the determinant restricted to this subspace will be R to the n minus 1, right? Okay. Fine. So, so then this Jacobian JVR, this is the determinant of d phi r at V. So by the chain rule, since phi r is a composition, this will be the determinant of this derivative of the exponential at RV. Okay. So going from the tangent space at RV to the sphere of radius R in the tangent space. So this tangent space is identified with V perp, mapping to gamma V prime R perp into the determinant of this, the derivative of TR restricted to TP1M. Okay. So this TPRM is the sphere of radius R in the tangent space. Okay. So this JVR is a product, right? So this second term here is just R to the n minus 1. So this first term I have to show this is equal to G of RV. Okay. Now, what is the difference between this term here and G? Okay, so, okay, maybe I should draw a picture, but otherwise this is getting quite cumbersome. So what I have is the following. So we want to show this. So we have G of W is the determinant of the derivative of the exponential at a point W. Okay. So where is this going from? This is going from the tangent space at W to TPM, which is identified with TPM, to the tangent space to the manifold at the image of W. Okay, so I'm looking at, this is my, so this G is a smooth function on TPM because the exponential is a smooth map. Okay. G0 is 1. Okay. And now what do I have? I have the following. So I have this unit tangent sphere, TP1M. Yeah. And then I'm taking a scaling T sub R, which is mapping this to a sphere of radius R. Okay, so this is 1. This is R. So this is TP Rn. Okay, and then I'm composing with the exponential, right? So this is going to the geodesic sphere of radius R. So I'm taking a vector V here, a unit tangent vector. Okay. And so this goes to RV, and then this goes to XRV. Which I can write as gamma V of R. Okay. And the composition of these two maps is my map phi R. Okay. And I'm looking at the derivative of phi R. So that goes from the tangent space here. So this tangent space, this is V perp. Okay. And to the tangent space to the sphere here, right? So here this normal vector, this is gamma V prime R, and this tangent space is gamma V prime R perp. All right? Yes?
Yes.
So my d phi R is going from V perp to gamma V prime R perp, all right? And I want to compute this determinant. So I'm breaking it up into 2 steps, right? So this V is going to RV by this map TR. The derivative of TR is mapping the tangent space to the unit sphere to the tangent space to the sphere of radius R, right? Okay. And this tangent space, this is also V perp, right? So the derivative of TR is acting as, again, as a scaling. It's just the map from V perp to V perp, whatever U goes to R times U. So the determinant of that map is R to the n minus 1. Is that clear? Yeah.
Yes.
And then I have to look at the determinant of the exponential map restricted to this tangent space, right? From this tangent space to this tangent space between these two n minus 1 dimensional spaces. So what will the derivative of the exponential map be? So actually, if you look at the picture, it's very clear. Instead of doing computations, which I've done in the notes, in the picture, it's very clear. You just take the normal vector to this sphere of radius R. That is the vector. So let me just oh, shoot, sorry. Aha. Okay, so. Yeah, so this normal vector is the vector V, okay? And this point is the point RV, okay? Now, what does the exponential do? So the exponential, it maps this straight line through the origin to this geodesic, right? So this tangent vector V, and it preserves length along the straight line. It preserves length along the straight line and length along the geodesic, right? So this unit tangent vector V here is going to go to the unit vector gamma V prime R, right? Yeah. So dxp at RV applied to V this is equal to gamma V prime R, right? Okay. And by the Gauss lemma, the derivative of the exponential maps this orthogonal complement here to V to the orthogonal complement here to gamma V prime R, right? Yes.
Yes.
So dxp at RV restricted to V perp. This goes from V perp to okay, so let me call this map A, all right? Okay, so let me call this map A. So this goes from V perp to gamma V prime R perp. Okay. And the derivative of the exponential at RV, it preserves the direct sum decomposition I have here, right? Which is RV direct sum V perp. This goes to R gamma V prime R direct sum gamma V prime R perp, right? So it preserves the direct sum decomposition, right?
Yes, sir.
So this map, therefore, with respect to this direct sum decomposition, this is an orthogonal direct sum. I can write it with respect to an orthonormal basis where the first element of the basis is V and the rest is an orthonormal basis of V perp. And similarly, I choose an orthonormal basis here which respects the direct sum decomposition. So with respect to that orthonormal basis, the basis of this derivative of the exponential will be block diagonal, right? With 1 here and A over here, right?
Yes.
Okay, so this implies what? This implies that G of RV, that is the determinant of the derivative of the exponential at RV, this is going to be 1 times the determinant of A, right? Okay. Which is equal to the determinant of A, right?
Yes.
Okay. And on the other hand, if I look at this picture above here, then the determinant, J of the determinant of d phi r at V, that's a product of these two determinants, right? From this tangent space to this one, this is dtr at V, and from here to here. So from here to here is the linear map A, right? So the derivative of d phi r at V is just going to be determinant of dtr at V into determinant of A, right? So this is going to be r to the n minus 1 determinant of A. And determinant of A we've seen below, this is equal to G of RV. So therefore we get that this is r to the n minus 1 G of RV. All right. Is this okay?
Yes, sir.
Okay, so that's it. So that proves the lemma, all right? Okay, so that's what I've written down in the notes here, but it's just easier to see in the with the picture, all right? Okay. So this Jacobian J of VR, I can write it as R to the n minus 1 times some smooth function G of RV, where G is equal to 1 at the origin, right? So in particular, if I look at the volume of the sphere of radius R, so this we saw that this is equal to the integral of the Jacobian JVR over the unit tangent sphere with respect to the volume measure of the sphere, right? D lambda P of V. Yes, we saw this.
Yes.
So this JVR is what? It's R to the n minus 1 times something which is close to 1 as R tends to 0. So this is going to be a big O of R to the n minus 1 as R tends to 0, right?
Yes.
Okay. And in fact, you can show more, right? In fact, the volume of SPR divided by R to the n minus 1, this is going to converge to a constant, which is the volume of Sn minus 1, right? As R tends to 0. Right? Because if I divide by R to the n minus 1, what will I get? I'll just get the integral of G of RV, d lambda V, and G of RV converges to 1 as R tends to 0. So I'll get the integral of 1 with respect to the volume measure of the unit tangent sphere. That's just the volume of the unit sphere, right? Okay. Is that clear?
Yes.
Yes, sir.
Okay, so this volume divided by R to the n minus 1, this converges to a constant, the volume of the unit sphere in Rn. Okay, fine. Now we want to get the following formula for the Laplacian of the distance function. So let, for a point P, let d sub P be the distance function from P, right? So we saw that this is smooth on M minus P, assuming that the exponential map is defined on all of TPM and is a diffeomorphism. And we saw that dP squared is smooth on all of M, right? Okay. So then we have the following formula for the Laplacian of the distance function in terms of the Jacobian. So at a point Q, this is equal to del J del R divided by J, okay, where Q is equal to x of RV, okay. V is a unit vector and R is a positive number, okay. So it's the logarithmic derivative of the Jacobian gives you the Laplacian of the distance function, all right. Right, this is del del R of log J, right?
Yes.
Yes, sir.
Okay. Okay, so how do we prove this? So, so we have this map phi r as before from the unit tangent sphere to the geodesic sphere of radius r. Okay, phi r of v is x of rv. Now, what is the Laplacian of the distance function? It's given by the divergence of the gradient vector field, right, of the distance function. So let's look at the gradient vector field of the distance function, right? So if I look at, we've already seen what this gradient vector field is, right? It's the radial vector field based at P, right? So I have the geodesic spheres based at P, and I have their orthogonal curves, which are geodesics starting from P. These geodesics starting from P are exactly the integral curves of the gradient of the distance function, right? Yeah, we've seen this already.
Yes.
Okay. So, so let psi t be the flow of the gradient of the distance function, grad dt. Okay. So what is this going to do? Well, it's going to map spheres of radius r to spheres of radius r plus t, right? So psi t of sp, well, psi t, not psi r, psi t. Psi t of sp r is going to be sp r plus t, right? Yes?
Yes.
And if I take a geodesic, say with direction v, starting from P, then psi t of gamma v r is going to be gamma v r plus t, right? Okay. Yeah. And if I take the map phi r, so this is defined from the unit tangent space to say the sphere of radius r. So this is phi r. And then I flow by time t by psi t, right? That's going to be the same as the map phi r plus t, right? Which goes to the sphere of radius r plus t, right? Is that clear?
Yes, sir.
Okay. Now, what is, so let's take a point Q equal to xp of RV. Okay. So this belongs to the sphere of radius R. Okay. So here V is a unit tangent vector. And R is positive. Okay. So, so what is the Laplacian of the distance function at Q? So we already saw that we can write this as ddt at t equal to 0 using the fact that this is the divergence of the gradient vector field. And the divergence of a vector field is the infinitesimal volume distortion of the flow, right? At time 0. So this is going to be ddt at t equal to 0 of the determinant of d psi t, right? At Q. Yes?
Yes, sir.
Okay. Now, all right. So what do we do here? Now, yeah, so now we use the direct sum decomposition. Okay, so so this psi t maps spheres around P to spheres around P, and it maps geodesic starting from P to geodesic starting from P. So if I look at the derivative of psi t, say going from, well, I have this tangent vector here and I have its orthogonal complement here, and I have this tangent vector here. I have its orthogonal complement here. This psi t is going to preserve this orthogonal decomposition, right? Yeah. So d psi t at q, this is going to preserve this orthogonal direct sum. So here, this direction is gamma v prime r direct sum, its orthogonal complement. And here it's r gamma v prime r plus t direct sum, its orthogonal complement. Right?
Yes, sir.
And this vector gamma v prime r is going to go to this vector gamma v prime r plus t, right? So that means this is going to be block diagonal with a 1 here and some matrix A here, right? Okay.
Yes, sir.
And yeah, so so if I look at this equation star here, right. Yeah, so see, this determinant of this phi r plus t here. So these are both mapping from, if I look at the derivatives, so this is my vector v, and then I'm looking at v perp here. So this d phi r and d phi r t are both defined on this v perp, okay? So by the chain rule, this d phi r plus t is the composition of d phi r together with this linear map from this tangent space to this tangent space, right? Which let me call this a sub t, okay? Right? So by star, d phi r plus t at v is equal to a sub t composed with d phi r at v, right? Yes?
Yes.
So now let me take determinants on both sides. So then I'll get jv r plus t is equal to determinant at into jvr, right? Yes? Okay. Right?
Yes, sir.
And now this determinant at from this block diagonal matrix, determinant at is the same as the determinant of d psi t at q, right? This is equal to determinant of d psi t at q, right? Okay.
Yes, sir.
So therefore, I get finally that Laplacian of dp at q, this is equal to ddt at t equal to 0 of determinant d psi t at q, and this determinant d psi t at q, this I can write as jv r plus t divided by jvr. So now when I take ddt with t equal to 0, I get del j del r divided by j, right? Is this clear?
Yes.
Okay. So that proves the lemma. Is this all right?
Yes, sir.
Okay. Okay, great. So we've got a formula for the Laplacian of the distance function in terms of this Jacobian. Okay. So, I mean, here, this is the same. Yeah, so this calculation here. All right. So now we can come to the definition of a harmonic manifold. Okay. So there are many equivalent definitions. We are going to take the one which is most convenient for our purposes. So we say M is a harmonic manifold if the Jacobian JVR is a function of R alone. So it doesn't depend on this unit tangent vector V. Okay, so that means J of V comma R is equal to just J of R for some function J from 0 infinity to R. All right. Okay, so this is our definition of a harmonic manifold. Okay. So immediately we can see some examples. So suppose M is equal to either Euclidean space or a rank 1 symmetric space. Okay. So in both of these above cases, the point is that the stabilizer K sub P of any point P in the isometry group, okay. So look at the isometries which fix a point P, right? So that's a group K sub P. This acts transitively on each geodesic sphere. So what's happening for Rn or for a rank 1 symmetric space is that the following. See, first of all, if M is any Riemannian manifold and you take a point P and M and you define K to be K sub P to be the stabilizer of P in the isometry group, let's say in the orientation preserving isometries. So then we always have a homomorphism from K sub P to the special orthogonal group of the tangent space, because every element G in KP fixes P, I can look at the derivative of G at P, right? So that's going to be a self map of TPM because G fixes P. And because G is an isometry, this derivative is going to be an orthogonal linear map. And because I'm taking orientation preserving isometries, its determinant is going to be positive, all right? So this lies in SO of TPM, right? Which is identified with SON, okay? And this map is actually injective because we know that if an isometry fixes a point and its derivative at that point is identity, so in a connected manifold, then the isometry must be the identity, right? We've used this fact before also,
Yes.
right? So that means that actually the stabilizer of any point is always identified with a subgroup of SON. right? A closed subgroup of SON. In particular, it's compact, right? Okay. Right? Is this all right? Yeah.
Yes, sir.
So in particular, this means that via this identification, this stabilizer, it acts on the unit tangent sphere because it acts on the tangent space by orthogonal linear maps. So it acts on TP1M, right? Yeah.
Yes.
Right. I mean, the action is just G dot V is defined to be DGP acting on V. Yeah, this is the action. So
We have just identified with the natural action of the special electron group. That's what you're saying. Now this injective form also.
sorry.
Look, we get the natural action of special electron group, and since this is just injective form also, so we are just identifying or restricting that action. That's what you're saying.
Yes, yes.
Right.
Correct. Correct. Okay, so the point is for M equal to Rn or a rank 1 symmetric space, this action of Kp on the unit tangent sphere is transitive. Okay. So you can take any unit tangent vector to any other unit tangent vector. Okay.
Hello.
Yes, we can hear you. Yes.
Sir,
Yes.
I got disconnected. My Zoom crashed. I am joining from my mobile, but Utsav said
Okay.
something.
Right. No, nothing. Yeah, it's just that
Okay.
you have this natural action because Kp is identified with a subgroup of SON, and SON acts on the unit sphere in the tangent
Yeah.
space. So this stabilizer K sub P acts on the unit tangent sphere, right?
Yeah, right.
This action is transitive, and so what happens is that this implies that if I call G equal to isom plus M, then this also acts on the unit tangent bundle via the derivatives. So this action is also transitive, right? Because if I have a unit tangent vector here, and I have a unit tangent vector at some other point, then first of all, I know the action of for a Rn or for a rank 1 symmetric space, the action of the isometry group is transitive on points. So I can first find an isometry which sends P to Q, and then V goes to some, under the derivative, V goes to some vector here. And then I apply an element of the stabilizer to move this vector to W, right? Okay. So the action on unit tangent vectors is transitive. And from this, it's easy to see that the Jacobian is independent of V, right? Is that clear? Because what will happen is you have TP1M and say TQ1M. Okay. So you have a sphere here, and you have a sphere here, and then you have these maps, phi r here and a map phi r here. Okay. Mapping to geodesic spheres. Okay. And I have an isometry sending V to W. Okay. And this over here, I have So this is the derivative of the isometry dg at P, and this is the isometry G. Okay. And this diagram commutes. And so you take determinants of derivatives in this diagram, and then you'll get that the Jacobian here is equal to the Jacobian here. Is it clear? Okay.
Yes.
Okay, so these will be examples of harmonic manifolds. Okay, so let me stop here and I'll see you next week. Okay.
Sir,
So-
next week, yeah. Next
So will
week
we have
when will-
class on Tuesday or Wednesday? You let me know.
Sir, and Thursday class, sir, I won't be able to attend the Thursday class.
On Wednesday, actually, there is one lecture by Professor Raghunathan from